Good morning, everybody. It certainly has been a little bit since I have done another video to help anybody that wants to learn a little bit of HVAC and how we go about doing things. So today we're going to get into a lot of ground, and that's going to be system diagnostics and troubleshooting procedures. We're going to be covering a lot of ground with this. But there's a lot of useful information that I am trying to convey to people, so to kind of help make your lives a little bit easier, especially those guys that are in the field, to find problems when it comes to a lot of your air conditioning stuff. So for this, we're going to be talking about a lot of diagnosing of air conditioning systems, and we're going to be covering airflow. We're going to be covering the refrigeration cycle, your condensers, liquid line restrictions, suction line restrictions, refrigerant undercharge, refrigerant overcharge, compressor inefficiencies, non-condensables inside a system, low condenser air entering temperatures, high condenser air entering temperatures, capillary tubes, and your TXVs. So, like I said, we got a lot of stuff that we're going to be covering. So, let's get into it. So, the first thing when it comes to air conditioning is that word, air conditioning. What are we doing? We are conditioning air. We're cooling it off. We're removing heat and humidity from that conditioned space. So, the number one problem that causes an air conditioner to not work as efficient as we would like is simply inefficient evaporator airflow. Okay? So when there is an airflow problem in an air conditioning system, it is usually caused by either too much air or too little air going across that evaporator. Now, assuming that the entire air conditioning system, or AC system as we usually call it for short, was originally set up properly, which means somebody came in there, did an air balance test, and made sure that we had the correct amount of CFMs coming out of each supply duct and our return ducts, too much air probably will not be usually like a problem area, right? Because it's set up correctly. But what's going to cause inefficient evaporator airflow? Well, it could be a bunch of things, really. Now, when we think about it, this is because air handling systems do not just suddenly increase or decrease air volume across their ductwork, okay? Now, airflow or air volume is calculated in CFMs. That is cubic feet per minute, CFM. Without some sort of outside help, that's going to cause that airflow to change. Now, a lot of causes is going to be like we say here. It's going to be a lot of dirty air filters. It's going to be faulty duct design just from the get-go, which is hopefully going to be caught in the beginning stages of installation or within the first maybe month or so of operation of this piece of equipment, that maybe there was a design flaw in the ductwork. Hopefully, if somebody's doing their math right and didn't forget a takeoff or a room, for example, in a home, hopefully the ductwork is designed correctly right from the very beginning. Other areas that's going to cause insufficient evaporator airflow is your loose fan pulleys if you have a belt-driven type motor. A slipping fan belt, just simply due to the fact that the fan belt itself is just old and deteriorated and just no good, not tight enough. A bad defective blower motor, for example, is another great example. Hey, if the blower motor isn't working at all, then hey, you're not going to move any air across that coil to begin with, which is going to open up another can of worms for us. Restricted ductwork a blockage inside the ductwork, closed vents, a rug over a return vent, maybe a couch over or blocking a return or supply grill or something like that, a dirty evaporator coil. For example, dirty or missing fan blades, which is always interesting. You know, maybe you have a fan blade out there that's actually literally missing a blade. Well, hopefully you'll figure that one out, because you'll hear the blower rumbling and shaking and doing all sorts of crazy shit. So they're out there, okay? Direct drive blowers going in the wrong direction, or maybe the wrong speed tap is actually connected, where we want to have, instead of it maybe being on high speed, you're going to want it on medium speed or medium low speed or whatever it's got to be for that particular type of air conditioning. Now, when it comes to your blower motors, a lot of our newer air conditioning, air handling systems don't have blowers in there that we can just simply change the speed by moving a wire up and down from high speed to low speed. We have a lot of ECM motors in there now, electronically communicated motors, which are now integrated into circuit boards. And those circuit boards now determine what speed that motor is going to be in. Those motors will now ramp up in RPMs depending on the load in the system. And as the load starts to decrease inside the home or space, the blower motor will now start to lower its RPMs to keep and maintain the correct amount of CFMs based off of the demand in the house. Another thing that we have to think about in regards to airflow is the required temperature difference across the evaporator coil. Now, why is knowing what your evaporator temperature difference is supposed to be for a particular application? Well, the first thing that we have to know is, what is temperature difference? Temperature difference is the temperature between your return air and your supply air. As that air goes across that cold evaporator, I am going to be removing sensible and latent heat from the air. I want that air to be colder as it comes out of my supply. But I can't have my supply temperature difference too great or too little. It has to be within a certain range. Okay, so some of your air handlers will have a chart like you see here, where it's basically taking a return air dry bulb temperature, which is basically the room air, and measuring your relative humidity within the air. So in order to take that measurement, the mechanic has to have a psychrometer with him. The psychrometer is going to measure the amount of humidity that is in the air. And what he can do is take those two temperatures and calculate what the temperature difference or temperature drop across the evaporator should be. So if the temperature difference is greater than the required temperature difference across the evaporator coil, there is most likely an airflow problem. Okay? The problem is not enough airflow, causing the air to stay in contact with the coil much too long and creating a greater temperature difference across the coil. Remember, air conditioning is air movement. We're trying to move the air at a certain velocity so that we can efficiently cool a space. So if the air is going too slow across the evaporator coil, maybe because of a dirty filter, loose pulley, or whatever, that's going to adjust my temperature difference. Okay? If the temperature difference across the coil is too less than the required temperature difference, the problem would be probably more likely a refrigerant issue. Okay? So this is because AC systems will not increase the airflow without some sort of malfunction or kind of human intervention. in there, okay? So, like, you know, maybe Mrs. Jones decided that she was going to close, you know, the supply air damper in her basement because she's never down there, or in her spare room because she never uses it. Those are types of things that are out there that can cause the required temperature difference to change. So really, what we do to understand how to use this chart is the first thing is we got to do is we got to know what the return air temperature is. So for example, this house is 80 degrees. Next thing is we got to figure out what the relative humidity is. Okay, in this case, we used our psychrometer, and we found out that we have a 60% relative humidity in the space. So what we do is we use those two calculations, and we find out where those two lines actually intersect. So we can see right here that our 60% relative humidity and our 80% cross right there. So we can look down here at our temperature drop of air across our coil, and we can calculate that we need at least, with these types of readings, that we need at least a 17.5 degree temperature drop across that coil. That is very good information for a mechanic because that gives us a ballpark of what we're looking at. Now, back in the day, it used to be 20 degrees, good for me. Okay, which means if you had a 20 degree temperature difference from your return and your supply duct, you were good. It was perfect. That's what we wanted to see. With newer stuff, that may not necessarily be the case because of that new technology that's out there. That blower is going to be ramping up and down. And as that blower ramps up and down, it's going to change the amount of CFMs across that evaporator coil. So my temperature difference is going to fluctuate based off of the demand in the house. Okay? So, now when it comes to the refrigerant cycle, we have to understand that your evaporator design also determines the temperature that you're going to be able to achieve. It's also going to determine your refrigerant pressures. Okay, we have larger evaporators, we have smaller evaporators. What is really important to know is the type of evaporator that you're dealing with. What size is it? Is it a large evaporator, or is it a medium-sized evaporator? Is it a small evaporator? What are we dealing with? Well, with larger evaporator coils, we obviously have a much larger surface area to contend with. Okay, the larger the coil surface area of the evaporator, the closer the coil temperature will be to your entering air temperature. Okay, the compression ratios also on these types of evaporators will also play a factor in what your evaporator temperatures and pressures are going to be. Okay, so that the compression ratio on your larger evaporators is also going to be decreased from the higher evaporator temperature and pressures, which causes the mass flow rate of refrigerant vapors through the compressor to increase. Now, why is that? Because now the compressor has to push that refrigerant through a much larger area. So when that happens, that evaporator is now able to absorb much more sensible and latent heat because it's bigger. So therefore, my temperature difference may not be as great as it would be for a smaller evaporator. Okay? The larger and more efficient the coil, the less temperature difference between the coil and entering air temperature. This causes your evaporator pressures to be higher and more efficient AC units. This changes the latent and sensible ratio of the evaporator. So we have to know that when we have larger evaporator coils, we really don't need as much airflow to go across that type of coil. However, if we have a smaller evaporator coil, we're going to need a little bit more airflow. So we have to be able to determine what type of system that we are honestly dealing with. Okay, condensers. Well, we know that the condenser is what's outside. It's our outdoor unit. That is what's going to be rejecting the heat that is being absorbed by the evaporator that is inside the home. Okay, condenser designs for larger capacity compared to your evaporator. Usually when you see those things outside, yeah, they look substantially larger than what is inside the house. The condenser and evaporator are very similar. So other than having different pressures and temperatures, condensers are usually a bit larger than the evaporator in order to handle the evaporator load, your suction line superheat gain, heat of compression, and your motor heat loads to the compressor. Just like the evaporator, the surface area of the condenser affects the design temperature difference between the condenser temperatures and your ambient temperature. Ambient temperature is what the air is outside. The larger the condenser, the more expensive it is to manufacture. But the EER will be much higher. EER is basically the rating of the efficiency of that unit. Okay? So with condensers, we have to be able to have enough surface area to be able to remove all of that sensible and latent heat from the space, but we also have to be able to remove the suction line superheat gain that is also being absorbed not only from the heat of compression from the compressor itself, because the compressor is a motor, it's going to run, it's going to generate its own heat, and the condenser fan motor. All of those things are all playing a part inside that refrigeration cycle. So if we have a condenser that's outside that is dirty and clogged with pollen and grass and all of that crap, that's going to cut down on that condenser's EER rating, its efficiency. It's not going to be able to achieve, and it's not going to be able to reject the proper amount of heat, which in turn will also affect the way the evaporator also operates and its ability to absorb all of that sensible and latent heat. Now, your liquid line restrictions, a lot of your common causes, if you have a problem with refrigerant flow, is probably going to be a restriction. Now, that restriction can be in the liquid line. Now, a lot of your common causes for that is obviously a restricted filter dryer on there, a restricted thermostatic expansion valve screen. Some of your expansion valves have a screen in there that can get clogged up from dirt and debris, especially if somebody, dragged the refrigerant line through a pile of dirt while they were installing it, or you got a burnout, or something going on inside the system that will cause these things to clog up. A kinked liquid line, which is very, very common. I hate to say it. Some people just don't know how to use a pipe bender or how to safely put a bend in a refrigerant line, so they wind up kinking it, and some people do it and they don't even realize that they kinked it. Kinked or a U-bend in the condenser coil. Soldering connections restricted with excess solder, so somebody doesn't know how to properly solder correctly. Usually a big old solder snot inside the liquid line can cause a restriction, or a oil-logged capillary tube if you're dealing with a cap tube. So a restricted liquid line starves the evaporator of refrigerant. That's basically what's going on when we have a restriction in that liquid line, which causes lower pressures in the evaporator. So if the evaporator is starved of refrigerant, you got to think about this. The compressor and condenser will also be starved. You're not getting the refrigerant back to the compressor because the evaporator just simply cannot absorb the correct amount of heat that is being rejected by the condenser. So it's basically almost, if you think about it, it's being overworked. It just doesn't have enough refrigerant in there to begin with to do what it needs to do. Most of the refrigerant will be in the condenser, which will not necessarily cause high head pressure because of the reduced heat load of the evaporator, which is a common misconception. A lot of people think, well, if I have, you know, a restricted liquid line, or I have a starved evaporator, my condenser pressures may be astronomically high because of, you know, I'm not getting the flow through. Well, that's not always the case, guys. Okay, you have to look at your entire operation of the system. When it comes to these things, you have to take the correct readings. You have to take superheat readings. You have to take subcooling readings. If you don't do those things, you're going to miss some vital pieces of information. Okay? Now, symptoms of a liquid line restriction. They can be local cool spots after a severe restriction from expansion of the refrigerant at that local pressure drop. Sometimes if you see ice buildup in like centralized locations along that liquid line, that's a sign of a restriction. If you take a temperature reading across a filter dryer on one end and on the other end, if you have a temperature drop across a filter dryer, that's a sign that the filter dryer is clogged up. You have a restriction. Okay, compressor amp draw will be low due to the reduced refrigerant flow. The compressor isn't working hard enough because it just does not receive the refrigerant that it needs. Bubbles in the sight glass, if you have one, if the restriction is before the sight glass. Okay, now sight glasses are optional in refrigeration and air conditioning systems. You may not necessarily have one, but if you see bubbles in the sight glass, there could be a chance that you have a restriction that is before that sight glass. Now, in terms of sight glasses, people will tell you, especially some mechanics that in many ways don't know what the hell they're doing, they'll tell you that, oh, it's good to see bubbles going through a sight glass. No. Wrong. Wrong. You do not want to see bubbles going through a sight glass. A sight glass is nothing more than a window to tell you whether or not you have a moisture-filled system or a dry system. That's all they're really for. They're not there to see whether or not the refrigerant is flowing and all that other shit. Okay? Which is a common misconception. High superheats is an indication from a starved evaporator. That's another telltale sign that you have an issue, that a possible liquid line restriction. Lower to normal head pressure in the system with a receiver due to liquid backed up in the condenser, but no heat load from the condenser to reject. If the evaporator cannot absorb heat, how can the condenser reject the heat? If one's not doing its job, how can the other do it? That's basically what we're getting at. You have to understand what you're dealing with when it comes to some of these things, guys. Now, the suction line may also be restricted in some cases. Okay? The suction line is much more sensitive than the liquid line because of vapor instead of liquid flowing through it. In order to understand what is happening inside a refrigeration system, you have to understand the refrigeration cycle. You have to know what the states of the refrigerant are throughout the entire system. You have to know the direction of flow through that system. Okay? A restricted suction line will cause low suction pressure. It's going to cause a starved compressor and condenser. It's going to be, it's also going to starve the compressor, which will lead to lower compressor amp draw because of its reduced load, and the condenser pressure will be low due to the reduced refrigerant flow and load. Which, in a way, kind of think about it, it really kind of makes a lot of sense. Back to what we were saying when it comes to your liquid line restrictions. If one is not doing its part, the other one sure as hell isn't going to do its part. Okay, so suction line restrictions, some of the symptoms that we can run into is really low suction pressure. It could be high suction, high compressor temperatures, a starved condenser, a flooded evaporator, or your condenser subcooling could be normal or even high. Okay, so if there is a suction line restriction, your liquid subcooling in the condenser will be normal, maybe a bit high, because a lot of the refrigerant will be in the condenser coil but will not be circulated very fast. Okay, because again, it's a roadblock, it's a restriction. The condenser subcooling may be normal to a bit high if there is a receiver in the system, and your condenser subcooling lets the technician know there is refrigerant in the system and that an undercharge of refrigerant can be ruled out. So that's why it's really important to be sure that you're taking superheats and subcoolings. Make sure you take those readings. You have to know what is going on with the refrigerant flow. That's telling us whether or not the refrigerant is flowing freely through that system. It's telling us whether or not we have the correct refrigerant charge in that system. And if one of those is off, that is a telltale sign that we have a refrigerant issue. Okay? So now, when it comes to refrigerant undercharge on our air conditioning systems, you're going to have low suction pressure, low discharge pressure. You're going to have a high evaporator superheat. You're going to have low condenser subcooling. You have bubbles in the sight glass, depending on the refrigerant type and system, and your low compressor amp draw. So, with low suction and your discharge pressures with high superheat in the evaporator are all indications of a refrigerant undercharge. Severely undercharged systems will run very low condenser subcooling because there is no refrigerant to subcool. Okay? If the subcooling drops to zero, which is we really don't ever want to see, the hot gas in the condenser will start to leave the condenser with some liquid, and bubbles will form in the sight glass if the system has one. Okay? So which is why we want to make sure that we're taking those readings. Now, refrigerant overcharge. You're going to have higher than normal condensing temperatures. You're going to have higher discharge pressures, higher discharge line temperatures, higher than normal subcooling, higher compressor amperage draw, higher compression ratios, lower evaporator superheat, especially if you have a fixed orifice type of system, TXV hunting or overfeeding of refrigerant. Okay, a system with an overcharge of refrigerant will have higher than normal condensing temperatures because of a couple of different things. First thing is because liquid backing up in the condenser. It's going to cause high subcoolings, and it's going to be robbing the condenser of useful condensing area. Okay? The elevated high head pressure will cause a volumetric efficiency of the compressor to decrease because the higher pressures of re-expanding volume of vapors in those clearance pockets of the compressor, it's going to cause that compressor to overheat. It's going to have higher amperages. Okay, your TXV will tend to overfeed or hunt. When you are looking at your gauges and you have your gauges on, if you see your head pressure and your low side pressure needles kind of fluctuating up and down, instead of remaining constant, that's a sign that the thermostatic expansion valve or metering device is hunting. It can't find that happy medium that it needs in order for it to achieve the correct temperatures and pressures. That's a sign of a refrigerant overcharge. Okay? With a 10% overcharge, liquid may enter the suction line and reach the suction valves or crankcase inside the compressor, and it can damage or cause the compressor to fail. So we have to make sure, again, that we are checking what we're seeing. Okay? Rule of thumb, when in doubt, check it out. Okay? Take some additional readings to see what is going on. Take that extra 5 minutes. Now, compressor inefficiencies, when it comes to this type of crap, you're going to have a higher than normal suction pressure, lower than normal discharge pressure. You're going to have lower compressor amperage draw, high evaporator superheat, and condenser subcooling can be maybe low or somewhat normal. Okay? Now, when it comes to this type of stuff, if the evaporator may not be able to handle the load due to your decreased refrigerant flow, okay, which can be either a overcharge, maybe an undercharge, the conditioned space temperature will start to rise if we have a compressor that is running inefficiently. The rise in return air temperature will overload the evaporator, causing high suction pressure and higher than normal superheat. So our refrigerant undercharge, our refrigerant overcharge can also cause our compressors to be inefficient. And when that happens, you're running at a much higher amperage. You're making that unit run harder than it absolutely needs to. Okay? Common causes of your compressor inefficiencies. They can be your defective suction or discharge reed valves inside there. Piston rings may have blown away if you have a semi-hermetic compressor. Defective capacity control if you're dealing with a lot of your commercial stuff. Leaky valves or worn piston rings are two of the most major problems that actually lead to compressor inefficiency. A symptom of an inefficient compressor is such high suction pressure and low discharge pressures. Okay, the conditioned space temperature is actually going to start to rise due to the refrigerant flow decrease. So we have to think about that, something that we got to keep in the back of our minds. When we have non-condensables in a system, non-condensables usually enter a system through poor service practices or leaks. Okay, non-condensables can be air or water vapor inside the system, and if we have non-condensables in there, they will take up valuable condenser surface area and cause high head pressures. Okay? Subcooling is also going to be high because the high head pressures cause a greater temperature difference between the liquid temperatures in the condenser and the ambient temperature. Excuse me, sorry. Okay, so a symptom of non-condensables is going to be high head pressure or high discharge pressure. You're going to have high subcooling. Your compression ratios are going to be high, and you're going to have high discharge temperatures. Now, low condenser air entering temperature symptoms are your lower than normal discharge pressure. Now, notice how a lot of these symptoms and stuff all stems around pressures. If my pressures aren't where they're supposed to be, there's a problem with the refrigerant, guys. Okay, low suction pressure, high evaporator superheat, low compressor amperage draw, high superheat, or higher subcooling, sorry. So, a 30 psi pressure difference is usually the minimum across a thermostatic expansion valve metering device. That's pretty much what we see. Okay? This reduces refrigerant flow, causes a starved evaporator, which will cause low suction pressures and high superheats. However, this may be also offset by increased subcooling at lower ambient temperatures. Okay? This entire drop that we're seeing in capacity may decrease the heat removal ability of an air-cooled condenser or of an air conditioner. So we think about temperatures and pressures in air conditioning, or hell, even in HVAC alone. The higher the temperature is outside, the higher the pressures I'm going to be expecting. Because in air conditioning and HVAC, temperature and pressure are going to coincide with each other all the time. The higher the temperature, the higher the pressure. The lower the temperature, the lower the pressure. So if I have low condenser air entering temperatures, I am going to expect to see lower than normal discharge pressures. I'm expecting to see a lower suction pressure. Think about an air conditioner that's running in the middle of winter. Okay? It's cold outside. What's going to happen with my pressures at my condenser? They're going to be lower because I have low condenser air entering temperature. It could be 20 degrees. We have controls in the field that will help take care of stuff like that because, you know, air conditioners can run 24 hours a day, 7 days a week, 365 days a year, but I have to have controls on there to help maintain a certain pressure inside a system. Low ambient controls, for example. So we have to think about a lot of different areas so far when it comes to diagnosing an air conditioning system. Air conditioning. If my air temperature isn't right, I'm going to be screwing up my pressures and my efficiencies of that unit. High condenser air entering temperature systems is going to be the complete opposite. I'm going to expect high head pressure, lower than normal refrigerant to air and ambient air temperatures, high compression ratios, low volumetric efficiencies, increased flash gas at my metering device, which is going to be reduced refrigerant effect, low superheat on your fixed orifice systems. Your high outdoor ambient temperatures will cause high head pressures to elevate. Okay? The temperature difference between your condenser temperature and ambient temperature will go down, and the refrigerant gas will not condense until the head pressure actually rises. The condenser cannot reject as much heat as this lowers your temperature difference and will accumulate the heat. The accumulated heat forces the condensing temperature to elevate to a temperature difference where the heat can be rejected. The temperature difference is the driving potential for our heat transfer, which is what we are actually trying to achieve. However, heat rejection on a higher condensing temperature will force the system to have higher compression ratios and therefore lower the efficiency of that type of system. So, your systematic troubleshooting, what a service technician really should do is have a checklist. The items that have to be measured. You should be taking a discharge temperature and recording it. You should be taking a condenser outlet temperature and recording it. Outlet temperature on the evaporator, record it. Ambient temperature, record it. Okay? Box temperature, what is the temperature of the house? Record it. Compressor voltage, compressor amperage, take your low side and high side pressures and record them. Okay? A technician must use the proper instrumentation and have certain organizational skills when it comes to troubleshooting, which in many cases a lot of mechanics seem to lack, especially those rookies. Those guys that have just came out of trade school or maybe have only a year of experience in the field. They don't have that sort of organizational skills and know what they should be doing during a service call. A service call is going to require you to take temperature readings, voltage readings, amperage readings, resistance readings, superheats, subcoolings, all of those things. Okay? By having a good organizational skill, by taking like stuff like this, is going to help you solve even the toughest problem more quickly. Okay, one way to be organized is to have a checklist, kind of something like you see here. Okay? We need to make sure that we're checking a lot of these things. Items that we need to be calculating, okay, is your condenser temperature split. Okay? What's the air going across my condenser coil? My condenser subcooling, my evaporator superheat, my compressor superheat. Calculated operating conditions are only accurate if measurements used in the calculations are obtained using obviously good quality equipment. Okay? We don't want to use something crappy. We want to make sure that we have decent meters and decent temperature thermometers and stuff like that to take these readings. The technician must take the time and follow the procedures recommended for your tools that you're being used. Now, what's nice is that we have refrigerant gauges out there that are now equipped with sensors, clamp-on sensors, where we can take a lot of all these readings all in one shot. So we don't have to have separate thermometers and stuff like that. It does the work for us. But we still need to be able to take those readings. Okay? Undercharge of refrigerant, you're going to see a couple different things. If it's undercharged, you're going to have medium to high compressor discharge temperatures, which means the discharge line is going to be extremely hot. Your high evaporator superheat, high compressor superheat, low condenser subcooling, low compressor amperage, low evaporator pressures, and low condensing temperatures. Those are all detailed signs of an undercharge of refrigerant. Overcharge of refrigerant, you're going to have high discharge temperatures. You're going to have high condenser subcooling. You're going to have high condenser pressures, high condenser split, temperature split across it, air coming across the coil. What's the air entering my condenser coil? What is the temperature of the air exiting my coil? You're going to have normal to high evaporator pressures, normal evaporator superheat, which always tends to kind of throw mechanics off, but it can happen, and high compression ratios. If you have an overcharged cap tube on these, you're going to have high discharge temperatures, high condenser subcooling, higher condenser pressures, high condenser split, normal to high evaporator pressures, high compression ratios, low evaporator superheat, and possible compressor flooding. Okay, there are two different symptoms between the TEV and your fixed orifice. Okay, low evaporator superheat and possible compressor flooding. That is the major two different symptoms between those two types of metering devices. Okay? Now, a dirty condenser or restricted airflow over the condenser, you're going to see high discharge temperatures, high condensing pressures, high condenser split temperature across the coil. You're going to see normal to high condenser subcooling. You're going to see normal to high evaporator pressures, normal superheat, high compression ratios, and a high amp draw on that compressor. Restricted liquid line after the receiver, you're going to have higher than normal discharge temperatures, high superheat, low evaporator pressures, low condenser pressures. You're going to see normal condensing subcooling, low condenser splits, maybe local cool spots or frost after the restriction, depending on where it is. Bubbles in the sight glass if the restriction is before the sight glass. Again, remember, the sight glass is optional. You may or may not have one. Low amperage draw or short cycling the low pressure control. Now, restricted liquid lines before the receiver, you're going to see high discharge temperatures, high condenser head pressures, high condenser subcooling, high condenser split, low evaporator pressures, low amp draw, bubbling in the sight glass, again, if there is one, and short cycling of the low pressure control. Now, what happens if you have air in the system? For example, a non-condensable. You're going to see high discharge temperatures, high head pressure, high condenser subcooling, high condenser split, high compression ratio, normal to slightly high evaporator suction pressure, normal superheat, and high amp draw. A restricted metering device is somewhat high discharge temperatures. You're going to have low condensing head pressure. You're going to have low condenser split, normal to high or slightly high condenser subcooling, low evaporator suction pressure, low superheat, low amp draw, and short cycling of your low pressure control. Now, when it comes to air in a system, and I completely forgot to even mention this, that if air is entering the refrigeration system, it's going to be because of possibly a leak, either through tubes, a gasket, or a flange. If you have a flare nut or something on there, you're going to have poor charging procedures, just simply because Joe Schmo didn't know what the hell he was doing in the first place. Poor recovery or recycling procedures. Maybe whoever did the recovery just didn't do it correctly, or had the system in a vacuum and took his gauges off and then closed the valves, or basically just being a stupid idiot, basically, is where you can really get a lot of air or non-condensables in a system. Forgetting to purge your hoses when accessing a system. Remember, that's one of the guidelines that we should be doing, is purging our hoses of any air or non-condensables that are in our refrigerant gauges before we hook them up to a system. When it comes to restricted metering devices, a restricted metering device can also be caused by a plugged inlet screen if you are dealing with a TXV, foreign material inside an orifice if it's fixed, oil logged from flooding, wax buildup in valves from wrong oil in the system. It can be sludge in moving parts from a compressor burnout, or it can be basically a manufacturer's defect in a valve or something like that is usually what's going to cause a restriction in a metering device. Now, if you have a restricted evaporator airflow, that can be wet vapor compression. Will take heat away from the cylinder, leaving the colder discharge temperatures. The evaporator does not absorb the heat load, reducing the load on the condenser itself, causing low head pressures and lower temperature splits. The TXV is going to lose control of the temperatures, therefore it's going to reduce your superheat. Liquid flooding will make the compressor cold and cause increase in the amperages on the compressor simply from the liquid slugging or the washed out of the oil on a system. So if you look at that sort of stuff, you're going to have a low discharge temperature, low head pressure, low condenser split, lower than normal suction pressure, low superheat, cold compressor case. If you look at the compressor itself, it may actually have some ice or looks like frost building up on it. High or normal amp draw. When it comes to oil-logged evaporators, the compressor, the first telltale sign is the compressor is going to be noisy. It's going to have a weird sound to it. Okay. Low oil level in the compressor crankcase, especially if you are dealing with a semi-hermetic compressor that actually has an oil sight glass on it where you can see the oil level inside the compressor itself. The TXV is going to be hunting. It's not going to be able to control the proper superheat. You're going to have low evaporator and compression superheat, and you're going to have inadequate temperature control, or better known as loss of capacity. So basically this system is going to be running all sorts of crazy shit, and it's not going to work correctly. Okay, causes of your oil-logged evaporators. It can be anything. It could be system piping, guys. Okay, not allowing the oil to return to the compressor. You can have superheat that's too low, which is going to cause compressor flooding. Inadequate defrost cycle on low temperature refrigeration, anything that is below 32 degrees. Wrong types of oil or too much oil, depending on what the deal is. When you have inefficient compressors, such as like a bad valve on there, you're going to have high discharge temperatures, low head pressure, normal to high condenser subcooling, high evaporator, low side pressures, low compressor amp draw, inadequate temperature control, and the compressor cannot pump down if you are dealing with a lot of your refrigeration and air conditioning systems. Main causes for your valves to be damaged is really liquid slugging of refrigerant or oil. Your superheat is too low, or the valves are weakened by acid or by overheating. That's usually what's going to cause bad valves in a compressor. Now, leak detection, evacuation, and cleanup. We have to do leak detection. We have to do that per EPA, okay? We have types or classes of leaks. We have evaporator leaks, condenser leaks, suction and liquid line leaks, pressure-dependent leaks. We have temperature-dependent leaks, vibration-dependent leaks, or combination leaks, which is really something that a lot of people don't really think of. It's like, oh, okay, it's a leak. Oh, it's probably going to be in the evaporator condenser, right? No. There are times where you're going to have issues with a system that has a leak, but that leak may not necessarily show its ugly face until the refrigerant lines reach a certain temperature, or if those refrigerant lines have been vibrating enough to actually maybe start showing its ugly face. So we have different ways of leak detection, and the first one is the most common, and that's your standing leak test. Okay? A standing leaks that can be detected while the unit is at rest, or it's off and it's fully equalized. Okay? This includes freezer evaporator coils warmed up by defrost. Okay? Standing leaks are the most common type of leaks that we have, or that we can possibly see. Your pressure-dependent leaks, these are the leaks that can only be detected as pressure builds up inside the refrigeration system. Nitrogen is used to pressurize the low side of a system to 150 psi, and on the high side to about 450 psi. Okay? Now, when it comes to leak detection, we want to use nitrogen. We never want to use oxygen. Okay? A pressure-dependent leak test should be performed if no leaks are discovered in the standing leak test. That's really, really important to know. Now, your temperature-dependent leaks, these leaks are associated with the heat of expansion. Okay? This usually occurs from high temperature ambient air, condenser blockages, or during defrost if you're dealing with a refrigeration cycle or a refrigerator. Vibration-dependent leaks are the ones that occur during unit operation. The mechanical strain of motion, rotation, refrigerant flow, or valve actuation are all associated with valve or vibration-dependent leaks. So what we can do, and if you see in this picture here, you can look at this part right here. This is an oil spot. This is a sign. This is a vibration eliminator that we can find on some of our commercial type of systems. The vibration eliminator kind of just helps eliminate a lot of the vibration that can happen on our refrigeration lines. But these guys here can also start to break down. So if you look right here on this dark spot, that is a sign of oil and dust coating on there. So there's a leak right here. But hey, we may not necessarily see that leak until that system turns on. Now, your combination-dependent leaks, those are flaws that require 2 or more conditions in order to induce a leak. Okay, now that is either between temperature, vibration, and pressure, causing the discharge manifold on a semi-hermetic compressor to expand and seep gas. That can be an example. It can be a flawed flare on there. It could be a cracked flare nut that has maybe cracked simply due to over-tightening or over-expansion or overheating, whatever. So now, with leak detection, we have cumulative micro leaks. Okay, individual leaks that are too small to detect with standard tools. The total loss over many years of operation slightly reduces the initial gas charge. A system having many fittings, welds, seams, or gasket flanges will have a greater amount of cumulative micro leaks. Okay, successful leak detection is really solely dependent on the careful observation of the mechanic. We're the ones that are out there doing these things. We're the ones that have to make sure that we're checking for these leaks and doing them properly. All refrigerant systems circulate compressor oil with the refrigerant. Oil will blow off with the refrigerant gas, and oil marks the general area of leaks. Look for oil staining. Look for oil staining and an accumulation of dirt in areas of the coils and vibration eliminators. Look around the compressor. If you see something like that, there's a chance that there's a leak there. Oil spotting is the technician's first quick check for leaks, but it will not always be reliable for some of the reasons. Oil is always present on Schrader valves and access ports due to the discharging of refrigerant hoses on the manifold and gauge sets. Okay? These parts are often falsely blamed as the main point of leakage. You got to put your gauges on them to see what the pressures are. So you're going to have oily residue around those areas, around your service valves and access ports. Okay? Oil blotches can originate from motors, pumps, and other sources, or may be the result from residue from a previous leak. Okay? Oil is not always present at every leak, though. Okay? It may take months, even years of operation to cause enough oil to blow off to accumulate on that outer surface. Okay? Oil may not be present with micro leaks. Oil may not reach certain leak positions. Oil may not be present on new startups. So we have to be very vigilant when it comes to leak detection. Okay, when we're doing an evaporator leak detection, the first thing that we got to do is we got to shut the system down. Okay, turn off all system power, including the evaporator fan motor. Wait for the system to equalize. Wait for the pressures inside the system to equalize. Now, use your soap bubbles. Use an electronic leak detector. And if you are using an electronic leak detector, put it on its highest sensitivity. Locate the evaporator drain outlet or downstream trap. Position the detector probe at the drain opening. Be careful that the detector probe does not come in contact with any water, though. Okay? If you put any water on the sensor, you just botched your entire effort to find the leak. Test a minimum of 10 minutes or until a leak is sensed. Recalibrate the device and test again. 2 consecutive positive tests confirms an evaporator leak. 2 consecutive negative tests rules out an evaporator leak. Okay? Refrigerant gas, and why we do stuff like this is simply because refrigerant gas is heavier than air. And gravity will cause the gas to flow to the lowest point. If the evaporator section is leaking, test should be positive from the drain. The technician should expose the coil and perform tests to pinpoint that leak. Now, if you have a condenser leak, calculate that electronic leak detector to the highest sensitivity and place the probe at the base of the unit. Cover the condensing unit with a tarp or bed sheet to serve as a barrier against any outside air movement and to trap any refrigerant. Okay? You're going to want to see what's going to happen. Okay? You're going to want to look at your leak detector. If there is a leak, it's going to go off. Because again, refrigerant is heavier than air. It's going to settle. What you're going to want to do again is make sure that the leak detector again has not been subject to water or any sort of debris or dirt. But again, if you have 2 positive test results, chances are the condenser is leaking. Now you're going to want to move on and try to find and pinpoint the actual location of that leak. Now, where you're going to want to look is where your screws are, because sometimes some guys put in screws that are longer than what need to be because they lost one in the grass, and they puncture a hole in one of the U-bends on the end of the condenser. Okay, it could be a minute little leak. It could be an actual pinhole where it actually leaked all the oil out. But you have to look at your areas of where these things may be. If you have suction and liquid line leaks, you're going to do the exact same thing. Okay, calibrate your liquid line, your electronic leak detector to its highest sensitivity. Place the probe at the base of the unit. Tuck the probe underneath a pipe insulation. Monitor for 10-minute intervals while the system is at rest or fully pressurized to equalization. It may be necessary to insert the probe at several downstream points. If the leak is sensed, strip away the insulation, apply soap bubbles, and try to pinpoint that leak. Okay? Suction and liquid line filter dryers are common causes of leaks. Solder and braze joints are common causes of leaks. Liquid line sight glasses should also be checked. Now, advanced leak detection under Section 608 of the Clean Air Act as per EPA. Mixtures of nitrogen and R22 can be used as holding charges or as leak test gases because in these cases the ozone depleting component is not used as a refrigerant. A technician cannot avoid recovering refrigerant by adding nitrogen to a charged system. Before nitrogen is added, the system must be evacuated to appropriate levels. The amount of R22 that's going to be introduced into the system need not be any more than that required for the detector to register its presence. That is per EPA. To ensure the 2 gases have mixed properly, bleed a minute amount of gas from the end of the system opposite to the point at which they were initially introduced. Okay? That is actually per EPA. Now, testing with pressure-dependent stuff. You're going to want to pressurize the low side to at least 150 psi and the high side to about 450 psi. The equipment rating plate usually states the maximum pressure permissible. Look at the nameplates on your condenser and evaporator before you do anything. Those numbers are your rule of thumb. Okay? Make sure that the valving and other components can take these pressures. If the high side and low side cannot be split by isolation valves, pressurize the entire system to about 350 psi. That's usually pretty good. Bubble test by thoroughly saturating all surfaces with your soap bubbles or foaming solution. Allow up to 15 minutes for reaction time for the microfoamer to expand into visible white or any sort of bubbles. Like you can kind of see here, like this receiver right here is actually leaking. You can see this little bubble right here. Check welds around the compressor. I have seen that a couple of times where the actual weld on the compressor was actually no good and it was leaking right there at the seam. Okay, so when we're doing a testing, a system-dependent pressure test, start at the compressor. Coat all of the suspected surfaces, including your suction line valves, filter dryers, and other components. With the system split system, check the outdoor section and then the indoor section. Do not stop leak checking as soon as a leak is found. There may be more than one, which is kind of common sense. Testing for temperature dependent leaks. Place the unit in operation. With condenser partially blocked, it's going to raise the temperature. With water-cooled condensers, use warmer water. Test the high side for leaks with electronic leak detectors in areas without air movement from your fans or bubble solution. Raise the evaporator or low side pressure by using warm water, placing the system in defrost, or heating it with a heat gun or something like that. And then test the low side for leaks using an electronic leak detector or bubbles. An electronic leak detector will not work if the air is moving over the suspected area of the leak. The area can be covered to allow the refrigerant to collect in a large enough concentration for the leak detector to actually sense that leak. So, testing for vibrations or a vibration-dependent leak. Again, put the unit in operation. Test for leaks with electronic leak detectors in areas without air movement from the fans, or use soap bubbles. Test all compressor bolts and gaskets. Test all line connections and fittings, and test all accessories connected to that system. Okay, those accessories are going to be your filter dryers, your pressure controls, your sight glass, vibration eliminators, pressure regulating valves, so on and so forth. Testing a combination-dependent leak. There are 2 or 3 procedures that should be merged into one. Suspect your valves or and fittings to high pressure. Spray or coat the suspected areas with soap bubbles, and then tap the component repeatedly with a rubber mallet to induce vibration. Again, you're going to want to check all of the accessories again, which is going to be your pressure controls, your sight glasses, your vibration eliminators, and your pressure regulating valves if you have them. You can also use a halide halide torch. You can also use a couple of different types of electronic types, which is a corona discharge type leak detector, thermistor, dielectric, ion, and all sorts of crap like that we can use. Your corona discharge type is detection of halogen gases occurs as a result of electron affinity. Ionization reduced the current flow. The sensor causes the detector to call into an alarm, and a pump induces the air sample into the sensor. Okay, this type of detector is made to detect fluorine and chlorine atoms in the refrigerant. Detecting fluorine is much more difficult than detecting chlorine. Major changes in tip sensitivity and circuit gain were required, and some detectors are designed with separate circuits and a manual switch for variable gains to sense CFC, HCFC, and HFC refrigerants. Your thermistor type of leak detector They have a variable resistor that varies its resistance in response to temperature change as gas passes over that sensor. Your dielectric type, these are going to respond to the different heat conductivity and or the dielectric differences between gases. So as gases are detected between the plates of capacitors, there are different dielectric strengths to change the capacitance of the capacitors, which is what sets them into alarm and tells you that you have a leak. Your ion type ionize or charges the gas as it is drawn over the tip of the detector. Okay, a transitionized electronic circuit board differentiates the gas and tells us whether or not it's actually a refrigerant or nitrogen or whatever it may be. Okay, electronic detector operation. Most electronic detectors have small fans or pumps that actually sniff or draw a sample of gas over their sensing tips. The sensing tips is passed over the suspected leaking source to sample the air at 1 inch per second. If a halogen refrigerant is sensed, the detector either causes an alarm to sound or lights will flash and goes all batshit crazy. And if the environment is contaminated with many refrigerant leaks, an ambient compensation device will compensate for the contaminated environment. Ambient compensation automatically calibrates the leak detector sensitivity to the ambient temperature surrounding the tip, and ambient compression makes the detector less sensitive, allowing the source of the leak to be pinpointed a lot better than having other issues or causing nuisance or false alarms. Ultraviolet fluorescent leak detectors uses a special fluorescent tracer additive and a highly intense black light lamp to pinpoint the exact source of the refrigerant leak. UV leak detections can be used for CFC, HCFCs, HFC refrigerant systems, and refrigerant blends using ester, alkali benzene, or PAG lubricants. Your high-intensity UV lights that provide a steady state intensity of at least 4,500 microwatts at 12 inches should be used. When we're dealing with fluorescent leak detectors, connect the appropriate pre-measured additive to the low-pressure refrigerant system service port. Open the valve slowly to gradually add the additive to the unit. Allow time for the additive to circulate, usually about maybe 10 minutes or so. Then you're going to use trace the unit with the UV lamp, and a bright yellowish green glow will show in the presence of all of your leaks. Your halide torch detection: when the refrigerant molecules contact the copper element in the presence of a flame, the color flame is actually going to change. As refrigerants are drawn into the flame, the refrigerant decomposes and the copper salts form. If a chloride salt is formed, a greenish flame will be produced. Can detect leaks up to as small as 0.7 ounces per year if conditions are ideal. However, when you are dealing with this type of stuff, you have to remind you that you are dealing with a flame. It is flammable and should not be used in explosive areas. When you're dealing with refrigerant dye leaks detection, when the system leaked, a bright red dye would be used to stain the source of the leak. Most of the time, the entire refrigerant charge must be replaced with refrigerant containing a dye additive. Some major compressor manufacturers will void warranties if the refrigerant with dyes are used in their compressors. So what you want to do before you start inserting any sort of dyes or anything like that to check for leaks, you want to make sure that you check with the warranty of the compressor or of that unit to see whether or not it will void the warranty. Most refrigerant dyes contain a mineral oil base. Many HFC-based alternative refrigerants require the use of ester-based or alkali benzene oils. Because of this, refrigerant dyes should not be used on ester-based or alkaline-based oil systems. Your standing pressure test: you're going to use dry nitrogen, and that can be used to pressurize the system anywhere between 125 to 150 psi or higher if your components actually permit it. A microfoamer solution, such as your soap bubbles, may then be used to leak test. A mixture of R22 and nitrogen can be used as a holding charge or as a leak test gas. When R22 gases is mixed with nitrogen, it allows us to find and fine-tune where the actual leak is. Nitrogen tank must always be used with a regulator, and safety pressure relief valves should always be in use. Never use compressed air with refrigerants for leak checking. The approximately 20% oxygen in standard air could cause an explosive mixture when mixed with many refrigerants if exposed to a flame. Ultrasonic leak detector relies on the sound or ultrasonic frequencies that the gas makes when it leaks. The sounds or frequencies can be caused either by gas leaking out or into an area. They are reliable in drafty situations, especially in outdoor usage, and some may be used with headphones to dampen background noise and amplify noise leaks. Can be safely used when combustible gases are present. Can be used on any type of refrigerant. Each detector has a sensitivity measurement or adjustment for small and large leaks. Some readouts may be in a decibel. It can be either analog or digital. Others will have a beeping sound that increases in intensity or frequency closer to the leak. Gases that leak in, like such as a vacuum leak, are not as easily detected as gases are not leaking out. When it comes to pinpointing a leak and monitoring, each of these two broad classes of detection have their own specific set of requirements and specifications. Leak pinpointers are used to check individual joints or components of a refrigeration system for leaks. Area monitors are used to check the level of refrigerant vapor present in an equipment room or for safety and leak detection. Sensitivity is defined as the input amount needed to create an alarm. Pinpointing detectors are rated in ounces per year. So pinpointing leaks can have a rating of as low as 0.25 ounces per year. Monitors can have an alarm rating of as low as 1 part per million to maybe 3 to 4 parts per million, which is usually the most common. Detector selectivity. Defined as the ability to detect only the refrigerant is of interest. Non-selective detectors are those that will detect any type of emission or vapor present, regardless of its chemical composition. Halogen selective detectors use the specialized sensor that allows the monitor to detect compounds containing fluorine, chloride, bromide, or iodide. Sorry, couldn't even say that damn word. Component-specific detectors are capable of detecting the presence of a single compound without interference from other compounds. Okay, so when it comes to a lot of things, you have disadvantages and advantages to obviously everything. Non-selective types of detection devices, they're usually pretty simple. They do have some ruggedness. However, they can be maybe a little bit expensive, such as like maybe about $250 to about maybe $1,500. Non-selective ones do have poor detection limits. They can be cross-sensitive to other species. Most cannot be calibrated, so on and so forth. So it depends on the type of application that you're really dealing with and what you're trying to achieve. Okay, some things here when it comes to the selectivity of them, some of them may be able to detect more than one refrigerant. Some of them may have a battery backup in case of a power outage. Some of them can be hooked up to an alarm. Some of them may not. It all depends on different types of things. Okay, so a couple of questions that I kind of run into. Why am I pulling a vacuum in a system? Well, it's pretty simple. When we pull a vacuum on a system, we're doing it to remove moisture and non-condensables. That's the main purpose of putting a system on a vacuum pump. What time span should I pull a vacuum for? Well, there is no real answer to that. It depends on the physical size of the system. Depends on the amount of moisture in the system. If you read the International Mechanical Code book, it tells us that we should really have these things on a vacuum pump for 24 hours at minimum. But, you know, in this field, time is money. You know, we got to make sure that we're getting our systems down to, according to EPA, about 400 microns. EPA states that 400 microns is considered a dry system. There is no more moisture and no non-condensables in there. Should I use a single or two-stage vacuum pump? Well, you know what? That answer is pretty simple. Always use a two-stage pump. Those are the best if you want to achieve deep vacuums. But why? Why do I got to put it in a vacuum? Why do I got to evacuate a system, guys? Well, guys, non-condensables, moisture. We don't want it. They're detrimental to a refrigeration system. You're going to destroy valves. You're going to destroy compressors. You're going to have screwed up metering devices. Non-condensables take up space inside the condenser. They're going to increase your head pressure. It's going to increase your discharge temperatures. It's going to reduce your subcooling. It's going to increase your compression ratio. It's going to cause moisture. Moisture in that system is going to have freeze-ups at the metering device. It can cause acid. It can cause sludge. All sorts of crap. Okay? Non-condensables take up space in the top of the condenser. That's usually where they're going to be. The liquid refrigerant forms a seal in the bottom section of a condenser, preventing non-condensables from passing or flowing through to the liquid line. They reduce the amount of surface area a condenser has available to remove heat from the refrigerant. Moisture freeze-ups can be hard to determine. There is no set time frame for a freeze-up. It can stop the refrigerant process for a few minutes or for a few hours over and over again. Moisture, oil, and high temperatures will create acids and then sludge. Physical size of the system or the internal volume. That's why we have to do things at time. How much moisture or air is in the system? It depends. It depends on the size of the vacuum pump. Okay? Vacuum pumps are measured in CFMs. How much can it move? What size line and hoses will be connected between the system and the vacuum pump? Obviously, we want to try to use larger hoses when we are in the evacuation process, but a 3-ton system will usually have an internal volume or space of 2 square feet or more for the refrigerant. So at 80 degrees dry bulb and 80% relative humidity, 1 cubic foot of air contains 8.91 grams of water. A system open to the atmosphere could have as much as 16 grains of moisture, more or less. Okay? There are only 456 grains per fluid ounce of water. So a system with an internal volume of 2 cubic feet will actually need approximately 30 cubic feet of air pumped out. So that kind of gives you a little bit of an idea of why time is needed to do a proper evacuation on a system. What is the required vacuum level? Deep vacuum is 29.9 or 500 microns. It cannot be measured with a compound gauge. For field work, a micron gauge should be used for measurements. Okay, at 500 microns, water will vaporize at negative 16 degrees. We can also use a temperature pressure chart to figure out what our inches of vacuum are, our microns, and our pressures are. So for example, here at 80 degrees outside, we are at 2,400 microns. When we are in inches of mercury vacuum, we are at 28.92 inches of mercury vacuum, okay, or 0.49 psi absolute. Now remember, 1 inch is equal to 25,400 microns. Okay, so a theoretical perfect vacuum is equal to 29.92 inches of mercury. Okay, or 0 microns, which is most likely never going to be achieved. Okay, so at 29.02 inches of mercury vacuum, or 22,860 microns, water will boil at 76 degrees. Okay, this seems like a warm enough temperature to remove all of the moisture, but it's not. So as the moisture in the system turns to vapor, it moves heat from itself and then the surrounding tubing, so on and so forth. It stops vaporizing until it warms up again. The lower the temperature surrounding the equipment, the deeper and lower the vacuum you will be able to achieve. Okay? A manifold low side gauge will not indicate an accurate vacuum level. We should never, ever, ever just go off of what your low side gauge says. All it's indicating is that we are in a vacuum. That's all it indicates. It's not telling us what we are actually at in regards of microns. Okay? System evacuation, as far as the evacuation pump. Okay, what size vacuum pump do I use? Well, a rule of thumb is 1 CFM for systems 7 tons or less. Okay? Your pump's CFM is rated for the largest intake fitting on the pump. 2-stage vacuum pumps can pull down to a lower level compared to a single-stage pump, and not using the proper procedures, hoses, and tools to connect the vacuum pump to a system will increase evacuation time. Okay? Vacuum pumps, size, rule of thumb, 1 CFM is good up to 7 tons. Your pumps, your CFMs is rated for the largest intake fitting on the pump. Okay, evacuation using standard 1/4 inch hoses, pulling through a Schrader valve, metering device, and accessories will increase the time required to pump the system down to the required levels. Not using a gas ballast for large systems or long pump run times can reduce the efficiency of the vacuum pump. Now, the gas ballast, what is its purpose? Okay, it helps keep the vacuum pump oil from becoming saturated with water vapor. Okay, most manufacturers recommend that the ballast stay open until the system is evacuated to a vacuum level of at least 1,500 microns. Okay, a properly maintained 2-stage vacuum pump will pull down to 50 microns or lower. When the gas ballast is actually opened, it allows surrounding air to be drawn into the pump and mixed with the air and moisture pulled from the system. It helps to reduce the amount of moisture transferred to the vacuum pump oil. The vacuum pump not only uses the oil for lubrication, it is used to seal the moving veins of the pump. Contaminated oil will greatly reduce the efficiency of the vacuum pump. The oil should be replaced each time after the pump is used to evacuate a system. And a 2-stage pump has 2 pumps in series, which allows the pump to pull to a lower level. The size of the system, the amount of moisture, your vacuum pump, so on and so forth, is all going to affect the time required for evacuation. Your manifold size and hoses, your valve core tools, all of those things are going to be a part of how long it takes for something to be evacuated. Okay? As stated before, evacuation using standard 1/4 inch hoses pulled through a Schrader valve, metering device, and accessories will increase the time required to pump the system down to the required level. Using manifold hoses of 3/8 inch or even 1/2 inch vacuum hoses, you're going to want to remove Schrader valve cores. You're going to want to open Schrader valves. may have a hole to open equal to about 30 seconds of an inch, and if you have any sort of solenoid valves, you want to make sure that those are energized and opened as well. Okay, when it comes to cleanup, vacuum pumps will not remove sludge, solid, or free water. Okay, water is removed as it vaporizes. Sludge, solids, and oils must be cleaned by using filter dryers. Depending on the type, filter dryers can be used to clean refrigerant and oil and capture foreign material, acids, and other types of moisture. So when the compressor motor burns out, for some reason, the high temperature arc causes the refrigerant oil mixture to break down into sludge, acid, and water. If the contamination forms from the burnout or the sludge compressor reaches the replacement compressor crankcase, the replacement compressor will probably burn out. Okay, the old method of flushing a system with R11 cannot be used because R11 is a CFC, which has a high ozone depletion potential. The new method of system cleaning involves the use of approved filter dryers, and the filter dryers incorporate the adequate desiccant to both the liquid and your suction lines.